So section 10.4 is on inscribed angles and polygons. So if you look at the word inscribed, it kind of has like a prefix in the actual word. So in, meaning like you're inside something. Inscribed, meaning like if you scribe something or a scribe writes. So this is literally you're writing inside or written inside angles. Then we'll talk about intercepted arcs as well. So an inscribed angle is just an angle whose vertex is on the circle. So in our example here, B and A and C, there would be vertexes. They're all on the circle. Right? We had central angles before where a vertex was from the center of the circle. Now they're on. Right? And then you'll notice that both of all the sides, no matter what angle you look at, they're all chords. So AB is a chord, BC is a chord, AC is a chord. So that's what an inscribed angle is made up of. A vertex on the circle and chords for kind of sides of the angle. When we make these inscribed angles, we'll have an arc, which is called the intercepted arc, which I just think of the arc that's between kind of our angle measurement. So if we're looking at angle B, we go from here to here, right? That's angle B. Our intercepted arc is kind of what's in between here. All right, what's caught in between. So our intercepted arc would be AC. And that's kind of what the second sentence says. An arc that lies between two lines, these could be rays or they could be segments, is called an intercepted arc. And then we have if the endpoints of a chord or arc lie on the sides of an inscribed angle, then the chord or arc is said to subtend the angle. So you would say arc AC subtends angle B, and then chord AC also subtends angle B. So that subtends is just a word really, to a way to talk about the relationship between an inscribed angle and whatever arc or chord is made from it. Right? Why that's important to know what inscribed and all those words mean is because we have a bunch of theorems that use those vocabulary words. So our first one, measure of an inscribed angle. So the measure of an inscribed angle is 1/2 the measure of its intercepted arc. So in our diagram here, we're looking at angle D, or we could call it angle ADB. Both would be good to say. All right, so the measure of angle D, these two are the same. So we talk about this guy right here. That's equal to 1/2 of the measurement of this longer arc here. All right, so for example, if this is 25, this angle measurement, this here would be 50. If this is 10, this is 20, if this is 100, this is 200. And we can go in reverse too. If we know this is 60, we know this has to be 30. We know this is 40, this has to be 20. It's kind of the difference between an inscribed angle and a central angle, where our central angles, our angle measurement and the arc measurement were the same. Now it's scaled up or scaled down by a factor of 2. So I'm going to make you change, we'll change just one at a time. This should be, instead of QR, it has to be QT. And then we'll change something in problem 2, but we'll do that when we get there. But we're going to find the two things. First, find the measure of angle T. Angle T is right here. And as we get used to it, I'm going to write out kind of the full version. So we're trying to find what this measurement is using this intercepted arc that angle RTS or angle T makes. So you could write this out as the measurement of angle T is equal to 1/2 of the measurement of your intercepted arc, which is RS. Again, the little swoopy hat on the top means it's an arc measurement. I'll zoom in more. And from there, we kind of just got to plug in what we know. We're trying to find the measure of angle T as our unknown. So that stays. And then we have 1/2. And then the measure of RS, was it 48? Yeah. So we plug in 48. We plug in what we know. That's 48 degrees specifically, because that's going to be our units. Our units is going to be degrees. So then you just take 1/2 times 48, or you're shrinking it by half. So the measure of angle T is 24 degrees. So this is where we solved for an arc measurement. Sorry, we solved for an angle. Now we're solving for an arc measurement. And again, it's a minor arc. It's less than 180. Just kind of keep using those vocabulary words. So we're looking for QT. That's this arc right here. So angle QT is subtended by angle R. So these two match up together. So again, you may just say, oh, well, this is 100 because you just double it. But if you want to write it out so you can get comfortable with it, you would say angle R is equal to half of the length of QT. And that's an arc, so we have our arc symbol. And then again, we just plug in what we know. Now we're given what angle R is. We're given that it's 50. 1/2 QT. So we're still, this is our unknown here that we're trying to find. So to get rid of the fraction on this side, we got to multiply by what's on the denominator. So you got to multiply by 2. So the measure of arc QT is 100 degrees. Right? It doubles its inscribed angle measurement. Twice as much. And that's all just from that first theorem. We're going to use this. That's probably the one that we'll use the most, and it'll be sprinkled into as we continue to do other sections throughout this unit. All right. Move on to the second example. The second example is going to lead us into one of our theorems that it's on the back page. This, if you're just, you got to change this. This took me a while to figure out what I wrote wrong. This has to be the measurement of an angle, not an arc. So cross this out. Instead of write measure of angle, STR. Or again, you could just say this is angle T, because we always look at these are our two other sides of our vertices. This is like our vertex. So let's first find the measurement of arc RS. So RS is from here to here. Since you don't have colors, what I like to do is just kind of make it more bold when you're drawing these, because I think it helps visualize what we're doing here. And we're trying to find RS. We're given, though, we look at this arc subtends angle U. So we can use a theorem we just learned on the top, that if this is 31 degrees, this arc, it should just be doubled. Right? So this is 31 doubled, this should be 62. So this right here has a measurement of 62 degrees. It still works the same way. The length of this arc is half of the measurement of the inside. So you could say the measurement of arc RS is 62 degrees. So now let's find this other angle. You go STR, which you go S to T to R. So that would be this angle right here in blue we're trying to find. We want to draw a little arrow. All right, well, using the same theorem, we would have to look, okay, well, I'm not given the angle measurement, so I'm going to look at I'm given an arc measurement. And it turns out angle STR subtends the same arc. It still subtends RS. All right. So that's going to help us because we could say, okay, well, right away, this has to be angle RSTR has to be 31 degrees as well because it'll be half of, then charge my computer now it's going to die. It's going to be half of 62, so this is 31. So our angle measurement, just like our other one, is equal to 31 degrees. So that equals 31 degrees. So there's our two answers. So really we could say is that angle T is congruent to angle U, which is going to be our theorem that's you flip on the next page once you're done writing, is really what the next theorem is getting at. So theorem 10.11, this theorem does just have a lot of chapters, not a lot of chapters. This unit has a lot of theorems, so we're already at 11 and we still have like 3 more sections, so we're gonna get up there. But if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So angle D and angle C in the diagram both intercept arc AB. So they're both half of the length of AB. So that means these two have to be equal to each other. You kind of want to do like the little, I think the dash marks are kind of helpful to like say, okay, well, yes. They both go to the same arc. So whenever you I always think of this as kind of like triangle, like your hourglass type shape, if you have something like that. These corner angles will always be congruent. We can say the same thing, that angle A is congruent to angle B, because angle A subtends DC, and B subtends DC as well. We both share this intercepted arc. So the next problem is it's almost too easy. It says, given angle E is 75 degrees, find the measurement of angle F. Well, it still kind of has that kind of hourglass type shape. It's really distorted though, but if we look, angle E intercepts GH, and angle F intercepts GH as well. So these two angles are going to be congruent to each other. We know this is 75. We know angle F has to be 75 as well. So you could say, given angle E is equal to 75, the measure of angle F is right at 75 degrees as well. And that's just from the last theorem. Because angle E, the measurement of angle E is equal to the measurement of angle F. So E is 75, F has to be 75 as well. All right. So now we're getting to the fun stuff, inscribing polygons inside of a circle. So we still have that word inscribed, literally meaning right inside. A polygon is an inscribed polygon when all its vertices lie on a circle. The circle that contains the vertices is a circumscribed circle. All right, circumscribed sounds like a different word, so don't say that word when you say it. It's circumscribed. All right. Circumscribed circle. It's a tongue twister. So we're going to circumscribe different polygons. Is just, a sided figure inside triangles, inside circles. In this case, it's a triangle. So inscribed right triangle theorem. So if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. So we have a right triangle inside here, and we see A to C is our diameter, because your diameter has to go through the center of your circle. Notice a triangle that has 3 sides. So it goes through our diameter. We can say, well, it's a right triangle. And then kind of the converse statement of that is, if one side of the inscribed triangle is the diameter, so this is the diameter, then the triangle is a right triangle, and the opposite of the diameter is the right angle. So the angle that is opposite of our diameter, remember opposite means like across our shape, go across from our diameter to angle B. So you can say angle B is our right angle, which would be our 90-degree angle. So just when you thought we were done with triangles, they come back. So we know this has to be our 90-degree angle. And you can kind of see that visually. Again, we never want to make assumptions when we're given a picture, but if it goes through, if one of your sides goes through the diameter, it's most likely a right triangle. And we have this if and only if statement, which means we can go forward and backward. All right. Next one. Now we're inscribing a quadrilateral, which quad meaning 4, so a 4-sided figure. So quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. And again, supplementary means they add to 180 degrees. And opposite angles means across from each other. Adjacent means next to. So E and G are opposite angles because they're across from each other. D and F are opposite angles. They're across from each other. So E plus G has to equal 180. So does D plus F has to equal 180 as well. We're C, and then C is just kind of our center. It can go through the center. It doesn't have to. We could draw a quadrilateral that has one of the sides as the diameter, and that would work. All right, so 2 quick last problems. We're going to find the value of each variable. All right, so in example 4a, just take a second to convince yourself what is your right angle, or is that even a right triangle, and convince yourself why. Is triangle ABC, is that a right triangle? Yeah, it is a right triangle because AB, you want to give you need to justify it for yourself. You can say AB is the diameter. So what that means triangle ABC is a right triangle. Again, you don't have to justify it like this each time. I just want to kind of show you why we can just jump to right away. Oh, it's a right triangle. Because if it's a right triangle, then the angle that is opposite of our diameter, so here's our diameter, AB, the angle opposite of it, go across, just like we did sine, cosine, and tangent. The angle opposite of the hypotenuse is always your right angle. So angle C then has to equal 90 degrees. So we could say that. That's kind of like our conclusion that we can make. Angle C is equal to 90 degrees. Maybe you want to draw your little half square. And we know angle C, we're given an unknown. We're given that that is 2x equal to 90 degrees. Well, we can figure out what x has to be then. Just divide it by 2. X has to be 45. The next example, we're dealing with polygons, and specifically a quadrilateral, where opposite angles have to be supplementary. So D and F are opposite angles, so Z plus 80 has to equal 180 because they're supplementary. So if you just kind of don't even have to subtract 80 from both sides, we know Z is 100 degrees. And then Y plus 120 has to be supplementary as well. So that means Y has to be 60. So these last two examples really bring back, we've talked about a bunch about triangles. Right, we spent a whole unit on triangles, interior angles of a triangle, sine, cosine, tangent, equilateral triangles that came up yesterday in one of the problems. And we spent a long time talking about quadrilaterals. Interior angles of a quadrilateral add to 360. We talked specifically about parallelograms and like squares and stuff. So this will be able to help you get started on your homework. The last two problems, I'll give you a hint. You have to use some like algebra maneuvers. So for the last two problems, you're either going to want to solve. You either have to use substitution or elimination. If you have no idea what those two things mean, let me know and I can talk you through it. See. 10.4 is the assignment. The keys should be posted, ready to go.
Go to the bathroom.
Yeah.